Okay, so put this in perspective here. Remember, what we're doing is we're gonna zip through. We'll get through this pretty quickly, but we're focusing on talking about how to solve quadratic equations. And we want to think about this strategically, right? We want to use a variety of different approaches depending on what the problem is. We've already dealt with probably the easiest one, which is when we can isolate x. But now we're moving on to some other kinds of situations where we can't isolate x anymore. And we already established the other day that if we want to solve something, let's take a real easy one. What if we had something like this? If we had x squared minus 3x minus 10 equals 0, we can't isolate x. There's a way we can make that work, but we don't know that yet. There are two different kinds of x's there, two terms with x's. They're not like terms, they don't combine, so we can't get a single x, right, at this point. So we can't isolate x. So what did we do instead?
Factor.
Okay, we factored, right? We wanted to break this up into a product of factors. And what is that? X minus x plus 2. Okay. And then why is that helpful? What's going on? Tanner, tell me. Need to wash that down with something? Okay, all right. Well, I don't want to make you joke. Isaac, help him out. He's too good back there. What's going on? Why is that helpful?
Why is what helpful?
Why is it helpful for us to factor that?
Alright, so you want me to still go?
Yeah, go ahead.
It's helpful to factor because one has to be equal. Oh yeah, that's right. One has to be equal to 0.
Okay, right. So what are our solutions going to be? Plus 5 or x equals negative 2. And the reason for that, remember the reason for that is what property?
Zero product.
The zero product property, right? The zero product property is what predicts that. We know that the product of two factors can only equal 0 when one or more of the factors are 0, right? So we just have to find the zeros of the factors. It's a great strategy. When it's easy to do, it's by far the quickest way to solve a quadratic equation. Now, sometimes it's either really hard to do or it's not doable at all, and then we move on to a new strategy, right? But for now, this is kind of what we're practicing. Okay, so what about this? What if we're asked to do something a little different here? This is really just a sub-skill of the process of solving a quadratic equation. If we're asked to factor the expression completely, we're just practicing that process of factoring. Okay, there's a couple issues that come up here, though, we've got to address. So, what do you think? What are we going to do with this one?
Make it negative 6.
Okay, we could take out a negative 6. Anything else? An x. Okay. So if we factor out, that is, what would we call that? All the stuff that we can take out. What do we mean? What do we call that? Greatest common factor. Right? So we're always going to try first to factor out the greatest common factor. Right? That's our goal. What's left behind if we do that? What goes here? 5x minus 9. Okay, how did you get those answers? How did you get the 5x? So, got too many answers. Somebody raise your hand. Help me out here. Brave soul. Yes, sir. Ty, how'd you get that? Okay, so well that's fine. So one way you could do this is you could just answer the question, if I were to, what am I doing when I factor out a greatest common factor? I'm essentially undistributing something, right? So if I were to redistribute, negative 6x times what would be negative 30x squared?
Why that?
5x, right? That's an okay way to think about it. So one way would just be to say, what would I need in these two positions to complete the distribution process, so I would get that back, right? What's another way? What's another way I could get that 5x? And I know this seems like a pretty simple thing, but it's actually, this will come up again, this idea comes up a lot in math. So how do I get from there to there? When I'm factoring out a greatest common factor, what am I really doing? Dividing. Right. Dividing by the greatest common factor, right? Everybody see that? So we could also say negative 30x squared divided by negative 6x equals what? There's my 5x. Right? There's the other way you can think about it. Okay? So is it crucial that this, could we also have said positive 6x? I mean, I guess, but I'm going to mark that wrong, because this is a really good habit to get in. Whenever you factor out a greatest common factor, you always take the sign of the leading coefficient, meaning the coefficient of the biggest power of x. So if we write this in, as we should, if we write this in standard form, and we haven't really talked a lot about standard form and factored form, we will start to do that more. But whenever we write out a quadratic expression, or later on polynomials with bigger powers of x, when we write it in standard form, we always want to put the biggest powers of x first, right? And so whatever the sign of that leading coefficient is, the number in front of the biggest power of x, that's the sign that we want to attach to the greatest common factor. So if the leading term is negative, in other words, the greatest common factor is negative. If it's positive, it's positive. Okay? Questions? Far so good, right? Nothing too profound there. This is a pretty easy one. We could probably even almost skip this one. Real quick, what's this going to be? If I want to write this in factored form, I'm just writing it as a product of factors, right? So what x? I heard x minus 9, x minus 8. Okay, no big deal. Okay, how about that? So let's write this in factored form. Fill in that blank. What goes there? Well, it's prime, so what would the factors of negative 5 be? There's really only a couple choices. Negative 5 and 1, or 5 and negative 1. Do either of those work?
No.
Okay. So if there are no magic numbers, what's that tell us? Well, it's already in factored form. This is what we would call I'm going to write this here. This is what we call an irreducible quadratic. We can't factor that, right? We can't factor it conveniently. We can't factor it and get back integer numbers, magic numbers in our factor, right? So the answer is what we started with, x squared plus x minus 5. That's what we'd enter in Moodle. That's factored form. Okay. Okay, what about something like that? Okay, that kind of steps it up a notch there. Now we've got a coefficient. So let's talk about what form is this in. Let's start to just, we're not going to spend a lot of time with this. But when we write out a quadratic expression in that form, there are many different forms of a quadratic function. If I write it in the form f of x equals ax squared plus bx plus c, we call that standard form. So we're starting off in standard form here, right? What are the values of a, b, and c?
343
Okay, 343, negative 30. Okay? So what do we always want to try to do first? Factor out greatest common factor. Is there a greatest common factor? There's not. Okay, other than 1, and we don't care about 1. So we're stuck with an a that is not equal to 1 this time, which makes this a little bit tougher. Now, how did you guys do this in Algebra 1? There's a variety of ways. I got a great trick if you haven't learned it. Do you know bottoms up? Okay, that's the way you do it? Okay. So you're already pretty familiar with bottoms up. Probably we should review that a little bit, I'm guessing, right? So what are the steps in bottoms up?
Can you explain what bottoms up is? Slip and slide.
So, okay, so bottoms up. Bottoms up is just a really quick, simple way to factor a quadratic, if it's factorable. Sometimes you'll find out they're not factorable. But you're going to factor a quadratic expression where a is not equal to 1. That makes it trickier, right? Okay, so the steps for bottoms up. Step 1 is you're going to find your magic numbers, right? Your magic numbers you get by finding, you have to find the product of a times c. So what's a times c? Negative 90. So we want to find numbers that add up to a times c, or excuse me, that multiply to a times c, and they add up to b. What's b equal to? 43. So the magic numbers must multiply to that and add to that. So we just got to find those numbers. We're going to multiply to a negative and add to a positive. What does that tell you about the numbers?
They're both negative. Smaller, bigger, positive.
Okay, so if they multiply to a negative, they have to be opposite sign, but if they add to a positive, the positive one is bigger, right? So we just have to go find those numbers. We have to find factors of negative 90 that add to 43. Now we know the positive one is bigger. So this can be pretty quick, but one way you can do this is you could just write a factor tree. So if we're gonna start with factors of negative 90, we know the positive one has to be bigger, so let's start really lopsided with the biggest one at 90. I want to show you a pattern here that's helpful. So we get 90 times negative 1, would you agree, multiplies to negative 90? What does it add to? 89.
We're already doing that.
Right, so it adds to 89. So now what? I'm just going to work my way down this. Okay, so now we want to see if we can make this one 2. Does 2 go in? Yeah, it does. So the next one would be positive 45, negative 2, and what does that add to? That adds up to 43, which is the winner. Right? Okay, but what if it wasn't? What if it wasn't? Let's just look at this trend. I want you to see something here that's there's a trend you can use that makes this process a lot more efficient. So what if I were to continue my factor tree? I could make this a negative 3, and I could make that a 30, right? I could make this a negative, I can't do 4, I could do 5. And this would be, what's that? 18. I could make this negative 6, and I could make that 15. What else? I could do 9, negative 9, and 10. Now I want you to notice what's happening to the sums as the factors get closer together. They get closer to 0. Right? And so so how can you use that to your advantage? If you're looking for factors by knowing what they need to add up to, it kind of gives you an idea where you want to start on this list. If they're adding to a number that's close to 0, you don't need to start with lopsided numbers. Start with ones that are closer together, right? Okay, make sense? Okay. All right. Something else I could say, but I don't think I need to. I'll do it later. That gives a pretty good idea. So we found the magic numbers. That's step 1, right? The magic numbers are 45 and negative 2. Okay, on to step 2. Step 2 for bottoms up is we're going to separate this into factors that initially look just like normal factors. So we're going to start with x's there and there, and the magic numbers, so here are my magic numbers. The magic numbers go here and there. Okay. Along with that comes step 3. Step 3 is whatever the leading coefficient is, we're going to divide each of the magic numbers by the leading coefficient. Okay? Is this ringing a bell? You remembering this?
Yes.
Okay. So what comes next? What do I do?
You slide it in front of it.
Okay, but before I do that, I'm going to try to simplify each fraction, right? So 45 divided by 3 is what? Okay, so that one's done, right? It reduces to an integer. This one we can't reduce. And then the last step is the bottoms up step, which is what? Okay, the 3 goes bottoms up. It goes from the bottom up front of the x, right? So if you have any denominators, you write those as coefficients. So last step.
Call me a magician dealing with these magic numbers over here. Then the answers. Right?
Step 5. Right. There's our answer. Okay? All right, let's try it. You try one of these.
Alrighty. Give it to me, boss.
Everybody good with that? Am I done? Okay, try one. Let's try.
Oh, loud.
Actually, let me do a different one. Okay.
Define young man.
Are you recording?
Yep,
Young man. This is big.
I can.
They.
They can.
Who is they?
Oh,
Just people
all
in the
kinds
class.
of all kinds of people.
What's that?
Mr. Oya goes viral for math questions.
It's about time. Okay, there you go. Try that. Try that. Try that.
No, that's not. That's a bad. That's a cool thing. That's too good.
Okay, what do the numbers need to multiply to?
96.
96. 3 times 32, right? They got to multiply to 96, and they've got to add to what? Okay, so what are magic numbers that multiply to 96 and add to 50?
48 and 2.
48 and 2. Right? So they go there, right? Okay, now what?
divide by 3.
Divide by 3. Okay, which reduces to what? X plus 16, X plus 2/3, and then last step? Bottoms up. Bottoms up is X plus 16 times 3X plus 2, right? Okay. On a test, what would I obviously do to check this? What would I do? We'll find out. Yeah, just FOIL it out, see if it works. Okay, what about this guy? Big magic numbers, huh?
Taking out,
Oh, there we go. What do I do?
take out a 4.
Very good. Okay, take out a 4. So first thing would be to take out a 4, which makes it look a lot easier in here, right? Then I end up with what?
Smaller numbers.
What would those smaller numbers be?
I got it right.
4x squared minus 5x plus 9, okay? Okay, so our numbers have to multiply to what? 36, right? Because now this 4 is no longer involved. A is equal to 4, B is negative 5, C is 9, right? So our goal here is we want to be able to break this down eventually into 4 times some other factors, right? And that's going to be our fully factored form. We're going to need to include that 4 though, because if it's in fully factored form, that means if I were to reverse the process and multiply it out or expand it out, I have to get this back. So the 4 is a part of our answer, right? That positive 4, that constant factor out front. But we got to figure out what the other factors are that have variables in them. So they multiply to 4 times 9 is 36. They add to negative 5. And what numbers do that? Okay, good. Negative 9, positive, oops, that can't be right. Oh, this one doesn't exist, does it? What do you know? Okay, so what is fully factored form going to be this time? It doesn't exist, does it? We can't find numbers. Thought we did. But they have to add to positive 36, or multiply to positive 36 and add to negative 5. There aren't numbers that do that, right? So what is fully factored form? That. I can take a 4 out, but I can't go any further, right? Okay? How about that one?
Oh boy, that's very.
Wow.
How about this guy? Take out a what?
-2.
A negative 2, good. It's got to be negative because the leading term is negative, right? What's that leave me with? What is that? 69x plus. Okay. So are we gonna have? We gotta get numbers this time that multiply to what?
68.
Multiply to 68 and add to.
68.
So what numbers are gonna do that?
68.
68 and 1. So we get negative 2 times x. Now, I don't even want to put an equal sign here. You tell me why. Because if I do this, usually what we would do if we're going to work our way down is we're implying that this is equal to this, which is equal to this. Is that true? It's not true, is it? We're going to go through a process of completing bottoms up, but until we get there, I can't really put that equal sign there, right? So What we're doing right here, all this stuff, I'm just gonna put all this in a box, and we're gonna ignore the -2 for a second. We're just working on this part. Oops. We're just working on this part. On simplifying that, factoring that. Okay, so we got the magic numbers, 68 and 1. Now what? Divide by what? 4. There's my 4, right? So I'm gonna divide each one by 4. And we're just working inside our box here to get an answer. So now what? (68/4). What do I do with that? Simplify. Got to reduce the fraction. So what's that reduced to? 17. So what does all that stuff become? Okay. So I get x plus 17 times 4x plus 1. Okay. So what is this actually equal to then? So this whole thing is equal to, I've got my -2 out front, and then I've got these factors. Okay, that's fully vectored for me. Okay?
Yes, sir.
Okay. All right, how about this? Okay, what does this mean? This is not a hard question, but I want you to understand what it's asking. If it says find the zeros of the quadratic function, this is a new thing. Have you guys did you ever talk about zeros? Because you did a little bit.
Yes, but let's review.
What are the zeros of a function? Okay, they're kind of, but you have to be more specific than that. They're solutions to an equation, but what equation? Because when we talk about solutions mean we have to have an equation that needs to be an equal sign. Okay, so right, there are solutions to the equation f of x, which in this case is 18x squared minus 15x plus 2 equals 0, right? Hence the name zeros. We're setting the function equal to 0 and solving. There's another way of thinking about that. If I wrote this function using function notation, so if I wrote this as f of x equals 18x squared minus 15x plus 2, what do I mean by that? Okay, so if I say f of 1, that's saying I'm going to evaluate this function when x equals 1, right? So I'm just going to substitute 1 in terms of how I get an answer. I just substitute 1 for x. So that tells me I get 18 times 1 squared is 18 minus 15 times 1 plus 2. So what's my answer? F of 1 equals 5. Good. So the value of the function when x equals 1 is 5. If I were to graph this function, we're not really talking about graphs of functions now, that'll be next unit. But if I were to graph this function, can you tell me a point that's on the graph of the function?
Just 0, 5, 0.
No. 1, 5. How come?
Oh,
Okay, how come?
x equals 1.
Think what we just said there. When we let x equal 1, the value of the function equals 5. Now, what's the job of a function? A function just gives us back a y value, right? You probably said at some point f of x is just a fancy name for y, right? I'm guessing algebra 1 you said that, right? That's all that's doing. It's giving us back y values when we plug in x values, right? So this function has the point 1, 5. Now, I want you to think about this in a couple of ways, because this is pretty important. We'll come back to this a lot. So if we're setting the function equal to 0, what are we really doing? The function gives us back y values. I'm setting y equal to 0, aren't I? Right? Now think about on the xy plane for a second. I want you just to ponder this. Where are all the points that have y values equal to 0?
The x
The
axis.
x-axis, right. So if we're setting up an equation, we're really just asking the math gods here with this equation. When we say where is the function equal to 0, what they're going to answer us with are solutions to the equation. They're going to give us the x values. So what are those? what do we call the x values where y is equal to 0? Sure, but what's another name for them? No, intercepts. What kind of intercepts? X-intercepts, right? Did everybody see that? Because if we're asking where does y equal 0, well, y equals 0 on the x-axis, and so we're finding the values of x where the function crosses the x-axis, right? So if we end up having real solutions, and we'll look at obviously some other examples where we don't have real solutions, but if we have real solutions to this equation, the real solutions, the zeros, the real solutions end up being x-intercepts, right? Now, if we get some other bizarre stuff, which we'll talk about, we're not quite ready for that today, but if we solve an equation like this and we get solutions that are imaginary, well, those imaginary numbers don't show up on the x-axis. So in that case, those zeros, if the zeros are imaginary, the zeros don't correspond to x-intercepts. But if they're real, they do, right? Another way to think about that then is, there's all these ways that kind of circle around the same topic. If I'm asking for the zeros of the function, I'm asking for the values. If I plug them in for x, what am I going to get back for the value of the function? Zeros, right? I'm trying to find the values of x that I can plug into this expression and get back 0. Just another way of saying that, isn't it? They all mean the same thing. Okay, how do we go about solving this equation? Well, we would set it up as this equation where it's equal to 0 and then go from there and solve it, right? What does that mean? Well, that's kind of stuff we've been doing, isn't it? Right? We're just going to try to factor this and then set it equal to 0. Okay? Does that make sense? So our goal would be to take this equation. Is it minus? Yeah. We just want to try to break this up into a product of factors, and then I can use the zero product property. Right? That's where the factoring, don't lose sight of that. That's where the factoring part comes in. And those will be our zeros. Okay, let's try that one. Let's solve that equation. So what am I going to do? Factor. Okay, good. Factor the left side. This is a different one. I already abandoned that one. I used that just as an idea. Okay, so leave stuff here. We go out to the track.
Oh, that makes sense.